Machine learning classifiers are moving into the center of security-critical systems. They are now used to navigate autonomous vehicles on public roads. We also rely on them to verify identity through facial recognition or to scan for malware in high-stakes network environments. The standard recipe for training these models is empirical risk minimization, or ERM. This framework finds model parameters, theta, that minimize the average loss across a distribution of benign data. While effective on benign inputs, models trained via ERM exhibit a structural weakness. They are vulnerable to adversarially crafted examples. An adversary can calculate a mathematically bounded layer of digital noise and add it to an image. The change is imperceptible to a human, but it shifts the structural properties the network relies on, forcing an incorrect classification. Building models that can withstand these inputs requires moving beyond specific defensive patches. We have to restructure the training objective itself to account for worst-case manipulations. This restructuring leads to a saddle point, or min-max formulation. We modify the ERM formula by inserting a maximum function into the loss. This inner maximization represents the attack, where an adversary finds the perturbation, delta, that maximizes the loss. The outer minimization is the defense, finding the parameters, theta, that minimize that adversarial loss. This single framework unifies prior work on adversarial machine learning. Every specific attack or defense mechanism can be viewed as an algorithm attempting to solve one half of this equation. This formulation provides a concrete security guarantee. If a network can solve this problem effectively, it will be resistant to any adversary that falls within the defined attack model. Casting adversarial robustness as a precise optimization problem allows us to evaluate security using principled mathematical tools rather than intuition. To solve the inner maximization, we must define the manipulative power of the adversary. We define a set of allowed perturbations, designated as S. For image classification, this is often an L infinity ball around a data point. Because the loss function is highly non-concave, finding the maximum loss is difficult. We use projected gradient descent, or PGD. This multi-step algorithm uses loss gradients to push an adversarial point away from the original image, iterating toward the boundary's local maximum. Weaker single-step attacks like the fast gradient sign method often fail to find these points. They cannot capture the complex nonlinear failure states that exist deeper within the perturbation space. PGD offers an exhaustive method for exploring this volume. It is currently the most reliable first-order tool for identifying a network's worst-case vulnerability. But we have to know if PGD is actually finding the true adversarial limit. Since the loss function is non-concave, does the algorithm simply get stuck in useless local maxima? This chart shows the loss values during 20 different runs of PGD. While they all start at random points, the loss values increase in a consistent way and rapidly plateau at a high, concentrated ceiling. The network fails in a predictable, clustered manner. After 100,000 random restarts, the results remain concentrated, with no extreme outliers significantly higher than what PGD typically finds. This concentration indicates that the inner optimization problem is tractable. PGD can reliably map the absolute performance ceiling of first-order adversarial attacks. Because PGD consistently finds these concentrated local maxima, it acts as a universal first-order adversary. Defending against it implies resistance to a wide range of gradient-based attacks. To complete the defense, we focus on the outer minimization, finding the model parameters that can lower this adversarial loss. Standard stochastic gradient descent cannot directly compute the gradient of the maximum function we've inserted into the loss. We apply Danskin's theorem to bridge this gap. The theorem states that the gradient of a max function can be computed at the specific point of the inner optimizer. We run PGD to find the adversarial point, then calculate the loss gradient at that specific location to adjust the weights of the network. Although the ReLU units in our networks aren't continuously differentiable, empirical results confirm that we can still use these gradients to minimize the overall risk and train more robust models. Danskin's theorem provides the link between the two loops, allowing the network to mathematically learn from the strongest available adversary during every step of training. However, mathematical optimization is only possible if the network has the architectural capacity to support the solution. For benign data, a straight diagonal line creates a perfect decision boundary, but adding L-infinity adversarial boundaries means the line cuts through vulnerable perturbation spaces. To separate these entire volumes without misclassification, the decision boundary must snake through narrow gaps, creating a complex, nonlinear curve. Small, low-capacity networks cannot converge on this objective. They lack the parameters to bend their decision boundaries enough to fit these new, tighter constraints. Achieving a robust classifier requires a significant increase in model capacity compared to standard training. To test this, researchers trained high-capacity networks on the MNIST and CFAR10 datasets using multi-step PGD as the inner loop adversary. This chart tracks adversarial loss during training. Instead of plateauing, the loss shows a steady downward trend over thousands of iterations. We see sharp drops in the curve that correlate exactly with reductions in training step size, proving the optimization is progressing successfully. This steady decrease demonstrates that the model is fitting the adversarial examples more accurately over time, steadily increasing its resistance. This provides evidence that deep learning models can be structurally hardened against first-order adversarial attacks. The final results show significantly improved robustness. When attacked with 100 steps of TGD and 20 restarts, the MNIST model maintains 89.3% accuracy. Even against the strongest iterative white box adversaries, the model retains nearly 90% of its accuracy. Against weaker black box and transfer attacks, these robust networks achieve accuracies over 95%, showing that transferability is largely mitigated. These robustness levels are achieved by training directly against the saddle point formulation, rather than relying on heuristic patches. Heuristic defenses often fail against iterative attacks, but solving the min-max problem through increased model capacity and universal adversaries offers a path toward deep learning models that are more reliably resistant to adversarial inputs.